Hello chemistry students, tonight we are going to be doing your final review. So let's get started here. Electron dot structure is our first thing that we want to talk about. And remember, this is just using your valence electrons from the periodic table. And that's about all you need to know. We find valence electrons from the group number on the top of the periodic table. And so I'll do an example here, like a chlorine is in group 7A on your periodic table, therefore it would get 7 dots. Okay, where something like sodium would be in group 1A, and so it would have 1 dot. Okay, now for the formation of an ionic compound, we can use the electron dot structure by showing the actual movement of the electrons from their orbital shell. So if this has 1 and that has 7, this one would go here, and you would have something that looks like this. This would be negatively charged now, and that would be positively charged. Okay. You could also show that by doing the crisscross method, but that would be an example using the electron dot structure. Okay, polyatomic ions, you just need to be familiar with them. That's mini atoms with a charge. You'll have your charts tomorrow, so you can look at them. They always involve oxygen, okay? And so just be able to identify those, and if they're in one of your compounds, recognize that and name it accordingly. Okay, so make sure you look over them just so maybe you're familiar with which ones you might need to use. Polyatomic ions are also very important when we're talking about naming acids. Okay, there's 2 types of acids. There's the binary acids that have no oxygen. Something that might really help you with this is that handout I gave you for naming. And then there's the oxyacids that obviously do have oxygen. And you name them a little differently. Okay, so if they have oxygen, they are a polyatomic ion. So the ending is going to be either ite or ate. If it is ate, you change it to an ic acid. So something I ate was ic. And if it's ite, you change it to ose. So us is ite. I think that's what Miss Oswald says. So that'll help you remember that. And they get no hydro at the beginning. Whereas binary acids, they do have hydro at the beginning, and they're always an ic acid at the end. Okay? So hopefully you can look in your book there, or that helps you refresh your memory a little bit. So if we had something like HCl, that would be no oxygen, so it would be hydrochloric acid, where if we had H3PO4, PO4 is a polyatomic ion that has oxygen. PO4 is phosphate, ATE, no hydro, so it would just be phosphoric acid. Okay. Ionic compound naming is very easy. You don't have, there's no prefixes. Okay, and the only thing you have to do is look out for 2 things: polyatomic ions, and you have to look out for things with oxidation numbers. Okay, and that's going to be something from the D block, and you would have to write it out accordingly. So like if you have Fe2O3, you would have to write that iron 3 oxide. Okay, so that's the only tricky thing there, and then being able to identify those polyatomic ions. Okay, metallic bonding, need to know what it is, the definition, and then where ionic bonds are a metal and a non-metal. Metallic bonding is 2 metals, okay, bonding together. Now, We call this the sea of electrons. And the sea of electrons just means that since all metals have are cations, which means they're positive, they have extra electrons hanging out, you're going to get a whole bunch of electrons. That's why they conduct electricity so well, and it's just the bonding of two metals. And when they bond, we call them alloys. Okay, so something like brass, stainless steel, and there is a chart in your book that has these different things on them, and you just need to know that they're different types of metal that are bonded together. Okay, so let's go ahead and go to the next page here. Oops. Formation of covalent bonds. This is dealing with the VSEPR models, so things like linear and tetrahedral, and that chart, that handout I gave you that has all of the different ones and how many bonding pairs and lone pairs that they have. Okay, we definitely need to know how to draw these, definitely need to know how to do the calculation. Okay, so there's trigonal planar and trigonal pyramidal, and then there's octahedral and bipyramidal, trigonal bipyramidal. Okay, and so I'm just going to go ahead and do like maybe one here for the calculation. So maybe we have, let's just say we have, oh, that's a bad example. That's okay. SO2. Okay. So SO2, we would, to do the calculation, we know that it has 3 atoms. So it either can be linear or trigonal planar. Those are only 2 options. So you need to know that handout to be able to figure that out. So we would go ahead and do our calculation. So we'd say 1 sulfur atom, because that's there's only 1. And in 1 sulfur atom, there are 6 valence electrons. We look at that on the periodic table. You add the second atom, so there's 2 oxygen atoms, and oxygen atoms have 6 valence electrons as well. So we have 1 plus 6 is, or 1 times 6 is 6, plus 2 times 6 is 12. So we're going to have 18 total electrons. Now we divide that by 2 to get the amount of bonding pairs. So we have 9 pairs of electrons. Okay. So right off the bat, just knowing about sulfur, I know he's going to act like oxygen. He likes lone pairs. So it's not going to be our trigonal planar. It's not going to be that flat structure that boron likes to make. So we draw sulfur in the middle, and we could just try a couple different things. We could try the bent, you know, like this, and we can put oxygen on the outside, and we could count how many. I guess bent could have been one of our, oh, I'm missing bent. There we go, bent. He could also be an option. So we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Since there's 9 pairs, we know that is not correct. Okay, so that one's no good. So we could try linear with a double bond, perhaps. So now we do this, and we get 1, 2, 3, 4, 5, 6. So we know 7, 8, sorry. We know that's not right. So this one must have a resonance structure. Okay, so that means that there's more than one way to draw it. And so we might have 2 draw it. Okay, so it's going to be a combination here of a single bond and a double bond. So we do this, we have 1, 2, 3, 4, 5, 6, 7, 8, and the other pair is going to be on top, 9. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we can also draw this the other way. So we would want to erase these two so I have some room here. Okay. There's all these little lone pairs. Okay, and so then we'd also want to draw it the opposite way. With the double bond here. And we put these in brackets. And we know that SO2, this is very poisonous, by the way. And so there's two ways to draw it, and so we would draw them both. And that's that. For naming them, naming covalent bonds, they have prefixes, all about prefixes. Okay, so that is your 1 is mono, 2 is di, 3 is tri, okay, so forth. 4 is tetra, and basically you put how many there are. So if you have C6H7, that would be 6 is hexa, so it would be hexa carbon, and then there's 7, so then it would be heptahydride. And everything has an IDE at the end, no matter if it's ionic or covalent, and except for if it's a polyatomic ion. Okay, there's a couple exceptions to this octet rule. Octet rule means there's 8 electrons in the valence shell. So with that calculation we just did, there might be a time where we get a 0.5, which, like nitrogen, he likes those lone pairs on top, but when he bonds with oxygen, okay, we have a unique situation similar to that one, and except for he just has a half of a lone pair on top, so which is 1 electron, and so we call that an odd number of pairs. So you just get a half of one, and that's usually something 0.5. So in this case, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 8.5 pairs, okay, which is considered an odd number. The expanded octet is one of those, like the PCl5, when it's the octahedral shape. Okay, we know we have 1 up, 1 down, 1 out to the side, and then 1 going back, and then 1 coming forward. So if we're going to do something like this, this is an expanded octet. That's way too many electrons for phosphorus to be sharing, but in special cases it does happen, and that's considered an expanded octet once I get all these electrons on here. And then the shrinked octet is just what it sounds like. There's not enough electrons. So boron is our example here, because boron here only has 6 valence electrons, or 6 shared electrons, when the octet rule states that you need 8, but boron's a moron, and so he only needs 6, okay, because of his placement on the periodic table. Alright, so polarity then is just the, I like to say, hogging of electrons. And so when you look at something, you see if there's one side that's hogging electrons. So in this case, I would say that this nitrogen, it's going to be polar because it has this weird electron, or if there's a double bond up here, it's going to be pulling electrons. This one, on the other hand, they're going to be shared pretty evenly, so this would be nonpolar. So like this one, these are nonpolar because they're all shared evenly, but another one that would be a similar shape could be like this right here. Now this is definitely polar because it has a majority of its electrons up here in the oxygen. So this side would be partially polar, and this side would be definitely a more negative side, where this one would be non-polar. Okay, so now that all kind of built on each other, and it was preparing us for this chapter 10, 11, and 12. And balancing the chemical equation was what we started off with. And balancing an equation, a couple really important things. Diatomic molecules. That is, remember, chlorine, fluorine, iodine, bromine, nitrogen, oxygen, hydrogen. That's pretty much the ones that we use. And so when they're using an equation like nitrogen gas plus hydrogen gas yielding ammonia, NH3, okay, we would have N, since it's diatomic molecule, it needs 2, because we